All right, let's just get right into it. If you're building AI agents at any kind of scale, I've got some bad news. Your instructions are probably costing you a fortune. So today, we are going to dive deep into how to optimize them for, and I mean this, massive performance gains. Seriously, if you're pushing LLMs into production, you're not going to want to miss this.
Let's just rip the Band-Aid off, right? This quote says it all. You know those super detailed, human-readable instructions you've been spending hours crafting? Well, they're not just helpful documentation. They are a bug, a really critical and very, very costly bug sitting right in your production environment.
So just how costly are we talking? Well, how does 40% sound? That's a potential 40% overhead. This number right here, this is the hidden cost of what we're calling chatty skills. And yeah, a number like that, it should make every single engineer and PM sit up and pay attention. So let's dig in and figure out what's actually happening here.
Okay, so this leads us to the big idea, our first key concept here, the hidden token tax. I'm not kidding when I call this the silent killer of performance and budget in your AI stack. And the scary part? It's almost certainly affecting you right now, whether you know it or not.
So, what is this token tax? Think of it like this. It's the overhead you're paying for bloated, wordy instructions. Every single unnecessary word, every please and thank you write for the model eats up your context window. That inflates your API costs, for sure. But worse, in a production environment where every single millisecond counts, all that bloat translates directly into latency. It's slowing your whole system down.
And look, it's not just about money or speed, as bad as that is. It's also about reliability. When you write instructions in plain English, you're introducing ambiguity. It's just inherent to natural language. And when you put that system under real stress during peak inference cycles, that ambiguity can cause something called logic drift. It's like the agent's mind starts to wander, straying from what you told it to do. And that leads to completely unpredictable and sometimes just plain wrong behavior. Not great when you're trying to scale.
So this all boils down to a central conflict we have to solve. It's really a battle, pros versus performance. The old, comfortable way of writing instructions versus a new, highly optimized approach that is all about one thing, raw, unadulterated speed.
And this right here breaks it all down. On one side, you've got legacy prose. Yeah, it's easy for us to read, it's familiar, but for the LLM, it's high latency and just full of dangerous ambiguity. On the other side, you've got dense markdown. This stuff is optimized for the LLM. It's high signal. It lets the model parse and execute instantly. And that is the mindset shift right there. You have to stop thinking of these as instruction documents and start treating them like high-performance code, because that's what they are.
Okay, enough about the problem. Let's talk solutions. How do we actually do this? How do we engineer this change? Well, let's get into architecting for speed.
It's actually pretty straightforward. It boils down to 3 core steps that any engineer can take. 1. Isolate the functional marrow. 2. Implement key-value mapping. And 3. Build recursive logic blocks. Let's break down each one of these.
All right, step 1, this is all about getting to the absolute essential core of your instruction. The goal here is to be ruthless. You are stripping away every single piece of non-essential linguistic fluff. The please do this, the extra little descriptive sentences, all of it. You want maximum semantic density. You have to look at every single word and ask, is this a direct, actionable command for the model? If the answer is no, it's gone.
Next up, key-value mapping. Honestly, this is a total game changer. So instead of writing out if the request is very urgent, you just create these super high-signal data pairs, something like urgency high. The model can parse that in a split second. But here's the really critical part. This rigid structure helps reduce positional bias. You know how LLMs can sometimes pay more attention to the first or last thing they read? This forces the model to weigh every parameter equally. Huge deal.
And finally, for the really complex stuff, you build recursive logic blocks. This is where the magic happens. It lets you define these really sophisticated multi-step behaviors. Think complex if-then-else chains, but without having to repeat the instructions over and over. It's how you build these incredibly efficient, compressed workflows that can handle just about any kind of branching logic you throw at them.
Okay, so theory is one thing, but what does this actually look like in the wild? Let's get practical. I think this next part is maybe the most important visual we're going to look at, a real, concrete before and after of this transformation. All right, so here's the before. This is a totally typical instruction for a customer support agent, right? It says something like, if the ticket is a billing issue and is marked as urgent, you should escalate it immediately to the finance team. Makes perfect sense to you and me. But for an LLM,
It is just loaded with useless tokens and, as we talked about, a ton of potential ambiguity.
And now, here's the after. Check this out. That exact same logic, compressed into one single dense line of markdown. Category, billing and urgency high, escalate, finance team. There's no ambiguity there. It's instantly parsable, and it is radically, radically smaller. This is what I'm talking about. You've just turned a whole paragraph of fluffy prose into a single line of high-performance code.
Okay, this looks cool, I get it. But does it, actually work? Let's get to the final act. Let's look at the hard proof, the data that backs all of this up.
Honestly, the results kind of speak for themselves, don't they? What you're looking at is a high concurrency stress test. We're pitting the legacy skill against the dense skill. And that difference in latency, look at the time to first token. It is absolutely dramatic. This isn't theoretical. This is the kind of real-world performance impact you should be aiming for.
So how is this even possible? It's simple, really. We've just slashed the prompt payload. Remember all that fluff we cut out? By doing that, you can get up to a 60% reduction in the actual size of the instructions you're sending to the model. And the math is easy. Smaller payload equals a faster response. It's really that simple.
And this all comes back to the bottom line, doesn't it? The performance gains, the smaller payload, it all translates directly into operational cost savings. We're talking up to 40%. Think about that. You get a faster agent, a more reliable agent, and you're paying a lot less for it every single month. That's a huge win.
So I want to leave you with one final question to chew on as you head back to your projects. As you're building for what's next for 2026 and beyond, you really have to ask yourself, is my AI built to scale, or is it just really well documented? Because frankly, the answer to that question is going to determine whether you're leading the pack or getting left in the dust by latency.